Okay, Sachin, do you have any question? Okay. Okay, so this is what I get now. If I'll take common, what am I going to get? If I take these things common, I'll get something like 2m 0 0 m whole multiplied with minus of omega square, right? Plus 3k minus k minus k k, this whole into cos of omega t into should I write it like a1 a2 cos of omega t is equals to 0 0, right? This is what I'll get. Correct. Now see, here I have multiplication. Firstly, I have a scalar value cos of omega t. Now my cos of omega t can be equal to 0 only for certain values of t, right? Only when my omega t is a multiple of pi by 2 or 3 pi by 2. Only in that cases my cos term is going to be 0. Not for all the time it is going to be 0. So I cannot consider it as 0. My A1 and A2 cannot be 0 because a vibration cannot happen if the amplitude is equal to 0. The amplitude should exist, and I've already assumed that my this whole term is actually my solution. So how can I assume that my solution is 0? It's a trivial case, right? And I'm actually trying to find out the non-trivial. I've assumed that my solution is a non-trivial condition. Okay, so I'm left with this matrix. Okay, so this is equal to 0. Then this means that this matrix, let us suppose B is singular. Now when I say that this matrix is singular, it means that the determinant of this would be equal to 0, right? So if I try to break this, what would I get? First I'll try to sum this up. Okay, I have these two matrices. I can sum it. Okay, and what would I get? I'll get a matrix something like 3k minus 2m omega square, and then I have a minus k k minus m omega square. Is it right? Let me just see. K minus m omega square. Okay, this is right. Okay, and what do I have? I have that determinant of this equal to 0. Right. So I'll now find the determinant. What is going to be the determinant? So it will be, I'm not audible. Am I audible now? Okay, is my screen visible?
Yes, madam.
Okay, now you can hear the voice, right?
Yes.
Okay, fine. Now if I find the determinant of this, what would it result? It would be 3k minus 2m omega square, k minus m omega square, minus of k square is equals to 0. Correct? This would give me 3k square, 3mk omega square minus 2k m omega square and plus 2 m square omega to the power 4 minus k square is equals to 0. Right. So what do I get now? 2m square omega to the power 4, and then I'll have minus 5 mk omega square plus 2k square is equals to 0. Correct? Now, if I try to find out the frequency in this case, so what is going to happen? Now, see, this is a equation which has omega to the power 4. So, for now, I can consider that my omega naught is equal to omega square. Okay, in that case, this will become a quadratic equation, right? So, what would I have? I'll have 2m square omega naught square minus 5 mk omega naught plus 2k square is equals to 0. For now I have assumed omega naught is omega square. For the ease of understanding that I am considering it as a quadratic equation, then I'll apply the formula of a quadratic equation to find out the root. And once I'll get omega naught, then I can get omega as well, because my omega would be under root of omega naught. Correct. So in that case, now I have this quadratic equation. Now I know that for a quadratic equation, what are going to be its roots, right? So also I can do one thing. I can just divide this whole equation with m square. Then this would dividing the equation with m square. What would it give me? Twice of omega naught square minus 5k by m omega naught plus 2k square by m square. This is my equation. Now if I want to find the root, its root would be its root would be 5k by m plus minus under root of 5k by m whole square minus 4 into, I have this twice of omega naught square, so I'll have 2 into, I'll have 2k square by m square, k square by m square whole divided by 2 times of a I have, so 2 into 2 would be 4. Clear? I hope this is clear. Okay, it is very easy. And this would be my omega naught 1 comma 2. Okay, so this would result in 5k by m plus minus, I'll have 5 into 5, 25, k square by m square minus 4 to the 8, 8 to the 16. 16 k square by m square whole divided by 4. This will be equal to 5k by m plus minus. Now 25 minus 16 is 9. Okay, I'll just write this step. 9k square by m square divided by 4, which would give me, now 9, when it will come out of the root, it will be 3. So I'll have 5k by m plus minus 3k by m divided by 4. So what am I going to have? 5 plus 3 will be 8. 8 divided by 2 would give me 8 divided by 4 will give me 2. So 2k by m. One option is going to be 2k by m, and the other one is going to be 5 minus 3, where I'll have 2, and 2 divided by 4 would be half. So it will be k by 2m. So here I got the values of omega naught 1 and omega naught 2. Correct? Now, since my omega was equal to under root of omega naught, so my omega 1 will be equal to under root of omega naught 1, which will be under root 2k by m, and my omega 2 will be equal to under root of omega naught 2, which will be k by 2m. Now, I don't think that I need to even discuss about why I'm not taking a negative value after root, because natural frequency can never be negative. Frequencies can never be negative. It should always be positive, right? So these are my two frequencies. Now you see here, as I told you earlier also, that if I introduce some extra mass, now if you see, if I consider this system, okay, what is its natural frequency? Omega 11, it will be under root k by m, correct? It is going to be under root k by m, perfect. And yes, for this also it is going to be, my omega 22 is also going to be under root k by m. However, now if you see, so if I consider, actually we don't have to know about this because this is a secondary system. We have considered this as a secondary system. So this is essentially a secondary system, means that it is a extra system that I've added into my primary system in order to mitigate the vibration. Right. So I'm not interested in studying the secondary system. If I consider the primary system, my primary system was first having a frequency of under root k by m. But after the introduction of the secondary system, if this is my primary system and this is my secondary system. Now, by the introduction of secondary system, you see that now my natural frequency has changed. And the both two new natural frequencies are not equal to the natural frequency of my primary system, isn't it? See, my natural frequency omega n for the primary system was what? It was under root of k by m. And the two new natural frequencies after introduction of the secondary ओमेगा क्या हो गया मेरा, ये हो गया 2k by m and k by 2m, correct? Now if you see that one of this is actually greater than under root k by m and the other one is smaller. Okay, so again it is going to show me a, if I plot the amplitude frequency response, initially the amplitude frequency response would be something like this, and after the introduction of the secondary system it would be something like this, correct? This is what the case is. This is what happens. So I'm basically changing the resonant characteristic of my system. Now changing the resonant characteristic, actually by this I can operate my primary system at its natural frequency with not taking it to infinite. Right. Now coming on to question number 4. Okay, for the system discussed in the previous question, which of the following relation between the modal frequencies is correct? Okay. So if you remember, I had my omega 1, correct? This was what I got. Okay. So, and if you see one, if I evaluate omega 1 square into omega 2 square, what would I get? I'll get 2k by m into k by 2m. 2 will cancel. I'll have k square by m square. So my correct option will be A. And omega 1 square plus omega 2 square, it would give me 2k by m plus k by 2m, which would give me 5k by 2m. So this would be my correct answer. Correct? So this becomes very easy, right? Now, question number 5 says that for the primary resonance condition, the value of the optimum tuning ratio and the optimum damping ratio, considering the mass of the primary system as 10 times of the secondary system is. Okay. So, firstly, I know that my primary system is M1. and my secondary system is M2. And what is given in the question? In the question, I know that my M1 is 10 times of M2. This is related to the secondary system. Correct. So I have this. Now, what does it say? It says to find the optimum tuning ratio. So as it has been discussed in the lecture, it has been discussed about the H infinity optimization. Okay, the H infinity. Though there are broad range of optimization techniques. However, the one that has been discussed in the lecture, I'll just consider that only. So for the H infinity optimization, okay, so if you remember, so what does it do? It actually optimizes the value of my tuning ratio which is also my control parameter. Okay, and my damping ratio. So it actually optimizes both these values in order to get the minimum amplitude. Minimum amplitude. Okay, at the resonance condition. Okay, so what does it do? It actually minimizes the maximum amplitude. Sorry. Or you can also say displacement of your primary system. What is to be taken care of is that we are only concerned about our primary system. We don't care about our secondary system. We are concerned about our primary system. Okay, so we are always talking about the property of my primary system. Correct? So, okay, so it's infinity optimization. So now this gives my ratio, and I'll just write the formula. If you want, you can refer to the paper also. Okay, it has been mentioned in the lecture also. So I have V optimum, which is my optimal tuning ratio. It is given as your 1 by 1 plus mu. The question is, what is mu over here? So mu is the ratio. Mu is the ratio of the masses. Mu is essentially M2 by M1, where my M2 is mass of my secondary system and M1 is the mass of my primary system, right? So it is equal to this, and my optimal damping ratio is given as under root of 3 mu by 8 into 1 plus mu. Okay, and now you know your mu is, we know that my M1 is 10 times of M2. So I'll have M2 divided by 10 M2. So I'll have mu as 0.1. Right. So if I put it here, I'll have V optimum is equals to 1 divided by 1.1, which would give me 0.9091, let us say, and my this optimal damping would be given as 3 into 0.1 divided by 8 into 1.1 under root. So this would give me 8 into 1.1. This will give me 0.1846. So these are my two answers. I hope that this is clear. This was a very easy question, and if you want to know that how are we actually calculating it, from where do I get this formula, so you can refer to the paper. Okay. or you can also refer to the lecture as well. Now coming on to question number 6. Now this example has been taken from the lecture itself. Okay, so this is a piezoelectric stacked actuator, and we have to first derive the equation of motion. So it would just take some time. I have considered in this in order to derive the equation of motion so that it would make the idea clear of how a piezoelectric material works. Okay, so let us first find the equation of motion. So as you can see here, I have 2 degrees of freedom. I have two masses m1 and m2 which are actually moving with x1 and x2. So first I'll make the free body diagram of mass m2. Okay, so what is m2 actually experiencing? It is moving with x2. It will first experience a inertia force m2 x2 double dot. Okay, maybe I should. It has k2 x2 minus x1. In the center, it is having your damping force c2 x2 dot minus x1 dot. Then over here, it is also experiencing a inertia force. Apart from that, there is also presence of what? Presence of a force due to the piezoelectric actuator. See over here, this thing. This is my actuator. Okay. I think my screen got freezed. I hope that it is visible now. Okay. So here, this thing, this circle that I am making is actually my piezoelectric stacked actuator. Okay. So this actuator, what is it actually doing? So it is actually sensing the movement of m1, and corresponding to that it is providing some force to m2. Corresponding to that it is actually trying to absorb the vibrations of m1, right? Mitigate the vibrations of m1. Okay, and if I draw, so there is a force. I'll just draw it over here, and I am writing it as fc, which is my control force. Okay, control force. How am I going to derive it? That I'll tell you. Now if I draw the free body diagram of M1. So what is my M1 experiencing? My M1 is going upward. So it will experience a force K1. Here you have M1 with X1. It will experience a force like this, which would be K1 X1. Apart from that, it is going to have a force because of the spring which is attached above M1, which is going to be your K2 X1 minus X2, or I'll just write it over here, K2, right? It is going to have a damping force C2 x1 dot minus x2 dot, a damping force over here also, which will be C1 x1 dot, and apart from that it is also going to have a again force which is due to the piezoelectric stack actuator, which is going to be your Fc. Okay, and then you're going to have a control, sorry, not control, inertia force m1 x1 w. Now I can write the equation of motion. First, if I write the equation of motion of m1, what is it going to be? M1 x1 double dot plus k1 x1 plus k2 x2 minus x1 c1 x1 dot c2 x1 dot minus x2 dot plus fc is going, acha, there is also this presence of an external forcing ft, so this will also be present over here. Okay, and if I write the equation of motion of m2, I'll have m2 x2 double dot plus k2 x2 minus x1 plus c2 x2 dot minus x1 dot, and this will be equal to your fc. Apart from that, now if I want to know what is fc, how would I know what is fc? So see, if you see over here, this stack actuator is something like this. It has some stiffness which is given like this, and this spring has a stiffness of K3. Right. Now, if you see that this stack actuator is going to have displacement of how much? See, there are only two displacements, x1 and x2. So definitely it is going to have a displacement x1 minus x2. Correct. But apart from that, if I assume that my stack actuator is actually having some initial displacement. Okay, it has some initial displacement. Let us say delta naught. Then in that case, I can write my Fc as, let us say here there will be some K, which would be, this K would be a result of the stiffness which the stack actuator has and this K3 has. Correct. So it will be K into x1 minus x2 plus some delta naught. I'll write it is some initial displacement of the actuator. Okay. Now the question is what would be K? So see, I have it, I can assume it something like this. One spring connected to other spring. This is K3 and this is Kp of E. So if I have two springs, one with stiffness K1 and the other with stiffness K2, I can find it its equivalent. I can find out its equivalent as K equivalent is equal to K1, K2 divided by K1 plus K2. So in this case, I'll have K as K3 KPE divided by K3 plus KPE. Simple. So this is how I wrote this force. Now my equation of motion is full-fledgedly complete. Okay. So now coming on to the next question. Now after the derivation, now you know what the system is. Now you know how it is performing, what we have done with the system, everything you know. Now we'll take these questions. Okay, so these are the some results which I have taken from the lecture itself, and this is from some research work which has been done by Professor Dwivedi's PhD scholar. Okay, so the question says that for the system discussed in the previous question, the frequency response is shown below. Now, which of the following is incorrect? It is asking which of the following is incorrect. Now, I'll just tell you that my alpha is actually my this tuning ratio, which I found out. I had a formula for finding the optimal tuning ratio, but my alpha is the tuning ratio. And this figure actually shows the variation of frequency response with my alpha. How is alpha actually changing the system properties? Okay. And here this the figure which is shown above it, it actually shows the variation of frequency response with damping ratio. Okay. So if you see over here, what is actually happening? I'll just write it. Variation of frequency response with damping ratio. So first, if I consider this figure, what is happening in this figure? If you see, if you look over here, Here I have three values of alpha, 0, 0.1 and 0.3. Now what do I observe? I observe that for my alpha is equals to 0, my system response is having a very high amplitude, right? It is having an amplitude greater than 6. Apart from that, omega is equals to 1 is actually the natural frequency of my primary system. Now, what was my main aim of introducing a secondary system in my primary system? My main aim was that I mitigate the vibration at the resonance, correct? But if you see for alpha is equals to 0, my amplitude is actually having, or you can say transmissibility ratio, is actually having a value which is near to 6. Correct. What does this mean? This means that what I wanted to do, which was mitigate the vibration, I was not able to do it fully. Correct. However, I have brought it from infinity to some value, but still the value is very high. Okay, so in order to mitigate it, I need to see how I could do it. So that is why for alpha 0.1, the response was plotted. So if you see for alpha 0.1, this is what I get. You can see over here that although my response has reduced for these two values, but for this, it is still greater than 1. If I consider that this is my transmissibility ratio is greater than 1. What does this mean? This means that if my forcing function is having an amplitude of, let us suppose, 10, then my system is going to vibrate at or with a frequency, let us, if I suppose it is nearly equal to 20, it is going to have an amplitude of 20. Correct? That is not what is required from me. I want to mitigate the vibration. I want the system to not oscillate. Okay, so what do? I further increase alpha. I increase alpha to 0.3. Now here you can see that now at omega 1, my transmissibility ratio or the amplitude has reduced a lot. It is now less than 1. So now I can consider that, okay, this could be an optimal option. Okay, this could be an optimal option because it has now reduced the vibration less than 1. The amplitude would be less than 1. So definitely it is going to be, or even if I talk about the transmissibility ratio, so if my forcing function is having an amplitude of 10, then my system is going to have amplitude less than that, which is fine. So we can say that it is optimal. Okay. Now if I consider this plot, okay, what does it show? It shows with the variation of damping ratio. So you can see that the variation of damping ratio, and as we know also, that damping has a very special effect. It is by the use of damping, we can actually mitigate the vibration by itself also. If you remember for a spring mass dashpot system, if I introduce a dashpot, it was able to damp out the frequency which was present due to the natural frequency of the system. Now, and also if I don't give any sort of a forcing to the system, the damping would make my system to come to a equilibrium state. Right. So here you can see that with the increase of damping value, my amplitude against the transmissibility ratio is actually reducing. It is also worth noting that with the change of damping, there are 2 points, omega and omega b, which the system is crossing. Okay, for whatever the value of damping ratio I take. Okay, so these are a constant points. Okay, so from this, what do I get? From this, I get that with the increase of damping, I'll have a decrease in the amplitude or the transmissibility ratio. And with the increase of my tuning ratio also, I'll see that there is a reduction of the amplitude or the transmissibility ratio. Right. So if I see now, see the options. The system does not show resonance condition for alpha is equal to 0. This is incorrect because it is showing somewhat resonance behavior. The amplitude is very high. Not very high, I would say high. The system response for alpha is equals to 0.3 reduces the resonance effect. Yes, this is the correct option. It reduces the resonance effect significantly because it has made my value to come to less than 1. Right. So the optimal tuning ratio and the optimum damping ratio is 0.3. Yes, this is the correct option because in both the cases I'm getting the minimum amplitude or minimum transmissibility ratio for 0.3, and 0.3 is your either the damping ratio or your tuning ratio. Alright. And then option D says there exist 2 points in the frequency response through which the curve passes irrespective of the tuning ratio. Yes, this is also correct option because yes, we have two values omega A and omega B which the curve passes, and this is common for all the curves that I have obtained for any value of damping ratio. I hope that this is clear. Okay, now coming on to question number 8. Now see, question number 8 says that the following results show the frequency response for two cases of feedback system. Which of the following is correct? Now first I'll talk about what is a feedback system. The feedback system, as we know, feedback means if I whatever the system is response it is showing, I take it, I take the response and feed it to the system. Right. Why is it required? It is required to improve the performance. Feedback to improve performance and achieve the required response. Correct? Now, if I talk about a feedback system, it is usually a control system. And when I say control system is actually, see, if I talk about a very sophisticated example of a feedback system, so a human body is the most complicated control system, correct? And how does the feedback system occur in a human body? So, if you'll go and touch a hot, let us say hot water or a glass which is full of hot water, steel glass. Okay, so steel, it would conduct the heat which is in the water. Okay, if you pour a boiling water in the glass and then you'll try to hold the glass, what is going to happen? What is going to happen? You'll see that within fraction of seconds, you leave the glass. You don't care whether it falls, whatever happened, you don't care. Okay, immediately within milliseconds, you're going to milliseconds is also a very high time, I'm saying within a fraction of seconds. Okay, you're going to leave it. And if you will realize that you are not able to think within that time. Okay, like if I'll see that, if I'll consider that my responses are based on my thinking, that is not what is actually happening. So what happened uh, in that very moment? So what happened was that as soon as you touch the glass which is full of hot water and the glass is also hot, what happened? Your hand is going to transmit the signal to your brain, neural signal. It is going to transmit it to your brain. Okay, and your brain is going to transmit another signal to your hand to leave the glass, to have a movement like this and leave the glass. So what happened? It was a feedback mechanism, right? Your the feedback was given through your hand to your brain. Okay, and your brain now gives another signal to your hand to just leave it. Okay, within very small amount of time. Okay, so this is how a feedback system operates. Okay, so what happened here is that depending upon how my system is behaving, how my environmental condition is, my brain is actually providing me signals of how I should be behaving. Okay, similarly, this can be true for my mechanical systems as well. Okay, I'll try to replicate this. For example, if I have a AC which has a automatic power cut, what happens is in that AC? I'll just put the temperature as maybe 25, and as soon as the temperature reaches 25 degrees, my AC is going to have a sensor. As soon as it senses that, okay, now the temperature of the environment where I'm operating is already 25 degrees, it will stop itself. It will stop operating. Correct. So feedback system was essentially introduced in order to save power, improve the efficiency of the system, and basically to reach the required response. Okay, like as a human, if I want that the temperature of my surrounding to be 30 degrees Celsius, and if my AC does not have a autocut mechanism and I don't have a temperature sensor, how would I know that it has reached the 30 degrees Celsius? How would I know that at what time I should switch off the AC? Okay, so that is why a feedback system is required. Okay. And the feedback system is also used in my mechanical or robotic system in order to see how the system should be given or what should be the given as an input to the system, so can does that I can get the required output. So it basically works on the error mechanism. What is the error? Okay, like in case when I tried to hold a glass which was full of hot water, what happened was my brain knows that the temperature that my body or my skin can sustain is, let us say, capital T. Okay, so it sensed that now the variation, that if my reference is capital T, but what I'm experiencing is some TH. So there was an error which was equal to T minus TH. This was my error. This was my reference, and this is what my uh, body is actually experiencing. So there was an error. So depending upon that error, my brain sent a signal that, okay, leave the class. Whatever happens, just leave it immediately. Okay, so this is how the feedback system works, and this is how we implement it in the mechanical system as well. So what happened in this kind of an actuator that was discussed over here also in this system, this piezoelectric stacked actuator, what was it actually doing? This was actually taking up the signal from M1, and depending upon that, it was providing some signal to M2. Depending upon the movement of M2, I was trying to mitigate the vibration at M1, right? So this is also a feedback system, feedback control system. Now, there could be two possible cases of feedback. One is my control, acceleration feedback control, and my second one is the displacement feedback control. Now, when I say acceleration feedback control, what does it mean? It means that I'm going to sense the acceleration which my body is encountering, and then depending upon that acceleration, I'm going to send the signal to the system. Okay, and in case of displacement, this feedback, I'm going to sense the displacement and then I'm going to send the required signal. Now, if I talk about these two, if I talk about anyways, before discussing this, let us see the answer, then I'll go through acceleration and displacement feedback. If you see over here, this was for method A and this is for method B of feedback control. Now, if you see for method A, as soon as I increase my alpha, what is happening to the system? When it was very small, which is 0.0001, I was having a very high amplitude, right? But as soon as I increased this to 0.5, it reduced significantly, right? And as soon as I increased to 0.99, this became almost a flat line. This became almost a flat line, which is beneficial for me, right? It means it is now controlled up to a very high amount. But if I see this for method number B, what is happening? For method B, you can see that from 0 to 0.4, my variation is significant. However, when I have changed alpha from 0.4 to 0.5, the variation is very small, or you can say it is even insignificant. So what do I see? I see that the higher value of tuning ratio, my method B is not able to mitigate the vibration that effectively. So what would I say? I would say that my method A is a better way of mitigating the vibration than method B. So I would prefer method A, right, for mitigation of vibration. So method A of feedback is better than the method B of feedback. Now over here, method A is essentially the acceleration feedback and method B is your displacement feedback. Now what happens in an acceleration feedback is, see, as the name suggests, acceleration feedback. It means that I take the signal of acceleration and apply counter force to mitigate vibration. Now see, if I want to know about a time response of a system, what would I like to know? I would like to know that how the displacement is varying with time, how the velocity is varying with time, and along with that, how the acceleration is varying with time. Correct. So in case of a vibration, if I know about the displacement, is it enough to tell about the system? No, it is not. Because my displacement is essentially varying in a sinusoidal manner. However, the thing which is actually making my displacement vary again and again is actually the acceleration. Correct. So in case of an acceleration feedback, what can I do is I can actually mitigate my high frequency vibrations as well. Right, because I know what is the acceleration of the system, because essentially acceleration is something from which I am getting the velocity and the displacement both. Right, it is not because of the velocity or the displacement that I'm getting an acceleration. Correct. Like if I have a mass and if I provided some acceleration, it is going to move. Up till which point it is going to move and up to what velocity it is going to achieve, it would depend upon the what type and how much amount of an acceleration is applied to the system. So if I know about how the acceleration is varying, I can know how the system is varying. So also you see that force, what my feedback system is doing is, if it is applying a counter force, my acceleration is what? My acceleration would give me a force if I multiply it with mass. So if I know the acceleration, I can know the exact force that is to be required at the particular instant to be applied in order to mitigate any kind of a vibration. If I can stop the acceleration, then I can stop the velocity and I can stop the displacement. But if I stop the displacement, it is not necessary that I can stop the acceleration. Correct. So that is why my acceleration feedback can actually mitigate high frequency vibration. While if I talk about my displacement feedback, so it takes up the displacement and then give the feedback. So this is very important for the steady state case, right? See, if I'll tell you that my system has some acceleration, okay, let us say A. I have mitigated the acceleration. Okay, fine. But what is the position that I want? I want my system to actually remain at a position x is equals to 2. But my system has mitigated the acceleration at x is equals to 1. Now my system would remain at x is equal to 1. But I want it to come to x is equals to 2. So my displacement feedback is it can be used for the steady state control. Because in my steady state, what would happen? In my steady state, my system is going to achieve a particular kind of a state. And if I don't want my system to be in that state, I would apply the displacement feedback. Right? I want the displacement to be this, then corresponding to that, it is going to apply the force and it would lead my system to that particular displacement which is required. And it is going to mitigate low frequency response. Low frequency response is countered. Okay, I hope that this is clear. Now coming on to question number 9. Now question number 9 says that considering the H infinity optimization, which of the following statement is correct regarding the mass ratio mu? So first, what is my H infinity optimization? So my H infinity optimization is a technique which actually minimizes the maximum displacement. Maximum displacement. Now from the H infinity optimization, I had two optimal values, relation of two optimal values. One was my optimal tuning ratio, which was given as 1 by 1 plus mu. And second was my optimal damping ratio, which was given by under root of 3 mu by 8 into 1 plus mu. So now it is asking that what can I comment or what is going to be the correct answer regarding the mass ratio mu. With the increase of mass ratio, the amplitude at natural frequency increases. Okay, so see. So you can see that my this and this both are a function of mu, mass ratio. First thing that you remember from the analysis should be for my primary system, for my primary system, I was having something behavior like this. As soon as I introduce my secondary system, my amplitude frequency response changes like this. So the first thing is that is to be kept in mind is that as soon as I introduce a secondary system, two new peaks are going to appear, and the value of omega at which these two new peaks are appear, peaks will appear, will not be equal to the natural frequency of my primary system. Correct? These two things are to be kept in mind. Now what is going to happen? First, I introduced a primary system. It led to change of the amplitude frequency response, something like this. Now, coming on to that, how it is going to vary with the mass ratio mu. Okay. So up till here, I know that I have introduced the secondary system, and my M2 is not equal to 0. Because as soon as my M2 is equal to 0, what is going to happen? If my M2 is equal to 0, the response is going to be like this only. There is no secondary system. Okay. So first thing is this going to happen. Now with the increase, now it is saying that how would it change with mu? So for now, I assume that my M1 is constant and my M2 is changing. So what is happening? Or it is also saying that increase of mass ratio. So my mu is increasing, correct? So I can say that my M2 is increasing. Now, if you see over here, if I talk about the optimal tuning ratio, if my mu increases, now since mu is in the denominator, my denominator term increases, due to which the optimal value of my tuning ratio decreases, correct? As mu increases, optimal value of this tuning ratio decreases. What does this mean? This means that what I was doing earlier for some value mu1, let us say that at mu1, provided mu1 was less than mu2, at mu1 I was having some v optimal 1. Okay, so and this v optimal 1 is actually greater than v optimal 2. So what is happening is that my actually objective was what? That I make the transmissibility ratio or the amplitude less, significantly very less. I should try to bring it to 0 or otherwise it is near to 0. Correct? So that objective was achieved for mu1 for V optimal 1 and it was achieved for mu2 for V optimal 2. And I can see that my V optimal 2 is less than V optimal 1, which means that my tuning ratio has decreased with the increase of mu2, which means that the amplitude actually reduces because of the increase of mu. Correct. Because my objective was same, constant. My objective was constant that okay, this is the level and I want my system to reach this level. Okay. Now if I required a V optimal 1, optimal tuning ratio 1 for achieving the objective, okay. So it was high as compared to V optimal 2 or sorry, this tuning ratio optimal 2. Correct? So the increase of my mu, which is the mass ratio, has actually led to the decrease of the amplitude. And that is the reason that now I require a comparatively less tuning ratio in order to reach my objective. I hope that this is clear. So according to that, my option 1, with the increase of mass ratio, the amplitude at natural frequency increases. No, B option is correct. Also, if I plot, see if I try to plot my mu and my this optimal tuning ratio, how is the plot going to look? The plot is going to look something like this. Plot is going to look something like this, something like this. So with mu, my V optimal is decreasing. Apart from that, it is also important that we consider the optimal damping ratio, which was under root of 3 mu by 8 into 1 plus mu. Now here also you can see that as my mu increases, this is going to reduce. And the plot, if I plot my optimal damping ratio with mu, the plot is going to be something like this. So you can see, no, yeah, you can see the plot as well. I don't remember how it is going to be. Anyways, so over here you can see that with the increase of mass ratio, the amplitude and natural frequency decreases. Also, there is one option, the amplitude is 0 for mass ratio 0. So this is not correct. As I told it earlier also, that the first thing that is to be kept in mind is that I have introduced a secondary system and my M2 is not equal to 0. Okay. If my M2 is 0, my mass ratio can be 0 only if my M2 is 0. Right? I cannot consider infinite M1. That is not possible. So my M2 is going to be 0. So if my M2 is 0, the amplitude can never be 0. It is going to be infinity. The system is going to have infinite amplitude if it is a linear system. If it is a non-linear system, then it is going to have some value. However, the behavior is also going to change. Our plot is not going to be in this straight fashion. It is going to show some bend in the amplitude frequency response. Okay. Now coming on to question number 10. Now see, in this whole live session, I talked about piezoelectric stacked actuator, but I didn't discuss anything about how it works. So I have taken this question so that I can make you understand that what is a piezoelectric stacked actuator. So first question arises is that what is a piezoelectric material? So my piezoelectric material is it is a very fascinating material, right? Now, a piezoelectric material has the capability that if I deform it, I take a piezoelectric crystal and I try to deform it. You know what is going to happen? It is going to produce a charge over its surface, which I call it as a direct piezoelectric effect. Okay. So what is going to happen? It is going to show two properties. First one is when upon mechanical deformation, if this is my input, what is it going to show? It is going to show some electrical charge is developed. This is my output. And this is known as the direct piezoelectric effect. Apart from that, it also shows the reverse piezoelectric effect. So what is going to happen if I apply electric field across it? This is my input. This is going to show what? This is going to show mechanical deformation, which is an output. And this is known as the reverse piezoelectric effect. Okay, so you can see that my system now shows two kind of a effect. One is a direct piezoelectric effect and the second one is the reverse piezoelectric effect. Correct? Now, how is it actually deforming? What is actually happening? So if this is, let us say this is my piezoelectric material, and if I deform it in this range, it is very important to note whichever direction I'm deforming it, it is going to develop charge in that direction only. And in the direction I'm applying a field, it is going to deform in that direction. Like for example, if I give a plus charge, minus charge, so it is going to deform in the thickness direction. It is going to lead to change in the reduction in the thickness. This is what is going to happen. Okay, this is my reverse piezoelectric effect. While in case of a direct piezoelectric effect, vice versa is going to happen, which means that if I have this and I try to stretch it in the thickness direction, what is going to happen? It is going to be like this, and now it will develop a charge. This is how a piezoelectric system works. Now, it is an active system. Now, when I say that it is an active system, if you remember, we had two kind of a systems, an active system and a passive system. A passive system had properties which were not changing. It was constant. My active system is going to change property, or it is going to show deformation on the application of some external force. Okay, so active system show change in property or deformation on application of some external energy. Like for example, we have electroactive polymers that show deformation on the application of electric field. Then we have MR fluids which show the change in the property with application of magnetic field. And these kind of all these kind of a system are known as active systems. Okay, so my first option it comes okay, multi-layer. Okay, so now this is how one piezoelectric material is going to act. Now, when I say stacked piezoelectric actuator, it means that I have multiple layers. I have this one layer, then I add another layer, then I have third layer, then I have fourth layer. Now, why is this required? Now, this is required because let us suppose that my one layer can give a contraction or extension up to some maximum amount, let us say Z. One layer can achieve maximum deformation, which could be expansion or contraction, okay, of Z, right? But I want, see, if I consider spring mass system, it may happen that due to the forcing, it can maybe oscillate between -5 to 5, or it can even oscillate between -500 to +500. But this has a limitation. It can deform only up to Z. And what if this Z is equal to 5? And what if my system starts oscillating from -500 to +500? In that case, I want that my piezoelectric crystal increases its maximum deformation. So what do? I stack different layers of piezoelectric. So what is going to happen? If my one layer is going to show a maximum deformation of Z, two layers are going to show maximum deformation of 2Z, three layers 3Z, and n layers are going to show deformation of NZ. Right, so now I have increased my deformation, maximum deformation from Z to NZ. So multi-layer, which we also call as stacked actuator, is able to achieve high higher deformation as compared to one layer. Okay, so if I talk about my first option, it consists of multi-layer of piezoelectric material and is an active system. Yes, this is correct. Absolutely correct. Second is displacement of each layer is additive. Yes, absolutely correct. Definitely. See, if my one layer is actuating by a small amount and my second layer is also actuating by that amount, definitely I can add it, isn't it? Definitely, I can add it. Right. So yes, it is additive in nature. Or I can actually show you like this. For example, if here is 1 and here is 2. Okay. Now my 1 changes like this and my 2 also changes like this. So what do I see? I should have drawn it here. Yes. What do I see? My 1 has actually shown some deformation, delta 1, and my 2 has shown some deformation, delta 2. So the total deformation of these two are going to be what? Total deformation of these two are going to be what? Total deformation of these two are going to be what? Total delta 1 plus delta 2. Correct? So yes, it is. The displacement of each layer is additive. This is also correct option. It deforms in the direction of the applied field that I've already discussed. Yes, it deforms in the direction of the applied field. And also the vice versa is also true. That is, when I deform it, it develops the charge in that particular direction of the deformation. Okay. Now it shows linear behavior. Now this is a very linear behavior. What do I know about a linear behavior? Any system, any physical system is going to show linear behavior only up to a certain level. After that, it is going to show a nonlinear behavior. So this comment that it behaves linearly, it is true. It is partially true because it is applicable only up to a small amount of deformation. As soon as my piezoelectric crystal, it actually leaves the threshold up to which it has having a linear behavior, it is going to behave highly nonlinearly. Okay, it is going to have a non-linear relation with respect to the applied field. While in case of linear behavior, it is going to have a linear relation with the applied field. So this is a wrong option. This is not correct. This is partially correct. It would have been written that it shows linear behavior up to certain threshold, then it could have been a correct answer. But it is written that it shows linear behavior, and for all the range up to which a piezoelectric material can work, it is not true for all the range. So definitely it is a wrong answer. Okay, so these are the 10 questions for today. And if you have any doubt, you can ask. And I hope that these questions will be helpful for you to solve the assignment problems. Also, I would like to mention one thing that if in case for the assignment question, you don't know what is happening or from where the reference is happening. So please refer to the lectures or either see the references that are mentioned in the your this assignment problem in order to see what is the correct option or not. Okay. And okay, so if you have any doubt, you can ask.
Thank you, madam.
Okay, thank you. I'll leave the meeting now.